Welcome to the afternoon session. The first talk will be by Professor Ali from Harvard, and the topic is topological string algebra.
Thanks, it's very flattering, but I'm not a professor. I wish I was. Okay, thanks. I want to thank the organizers for giving me the opportunity to talk here and talk about this work in progress, which I'm pretty excited about. But the title is still pending, so it has to do with topological strings and it has to do with the Lie Algebra, what will be eventually called still pending. And this is work with Movasati, who's at IMPA in Brazil and currently visiting Harvard, and Emmanuel Scheidegger, who's today actually teaching in Freiburg, and Jul1Tue now. Okay. Let me start with motivation. So many talks of the conferences actually benefited from a fruitful interaction between math and physics. And the one set of ideas or the one line of thought that I want to highlight is, which led to many fruitful interactions, is to think about physical theories in terms of deformation families. And then think of the whole physical theory together with all its deformation space. So this gets translated mathematically into geometries and their moduli spaces. So the benefit for math from this is that physically many theories, there are dualities, there are the same theories which lead to different mathematical constructions. And then by default you can use physical intuition to say, okay, if this leads to the same physical theories, then actually the equivalent mathematical structures together with their deformations or moduli spaces should be the same. So for the purpose of the talk, I want to concentrate on mirror symmetry for Calabi Yau threefolds. So X and Y will be a mirror pair of Calabi Yau threefolds. And mirror symmetry identifies deformation families of both sides. So the deformation family on the left-hand side is a little bit more difficult mathematically to trace. So it's a deformation of the complexified Kähler structure. And on the right-hand side is the deformation family of complex structure of Calabi Yau threefolds. Okay, then eventually, so what does this mean? So identifying families of Calabi Yau threefolds, but eventually you also want to identify structures and interesting functions or whatever you want. You want to be able to identify on the two spaces. One quantity that I will focus on is this topological string partition function. There have been many talks about knot theory. So you can think about this, if you pick the right Calabi Yau threefolds, then this object will also know about your knots. So for example, in Professor Zagui's talk this morning, there appeared some infinite sum with an H, so well, physically with an H bar. And you can think of this as the object that will give you these invariants. Mathematically also, so these are global objects on these moduli spaces. And mathematically, some limiting points on the moduli spaces are of particular interest. For example, on this side, there's a limiting point where these objects here reduce to generated functions of Gromov Witten invariants. Okay, so what I want to talk about is what are the mechanisms that we use and what is their physical origin that allow us to actually put coordinates on both moduli spaces and match these and then also match the things we compute on both sides. So the way this worked for genus 0 mirror symmetry, or just the curve counting, is to physically translate the sum variation problem that you consider on top of this moduli space, and then find its mathematical counterpart. So the mathematical counterpart for this case was a variation of Hodge structure. So if you're able to trace the variation of Hodge structure on both sides, then you can start using physics to map the two things to each other. What I want to talk about today is a way, or propose a way, to specify the mathematical problem, or some more rigorous way of specifying what thing you should be looking for in order also to identify the variation problem that happens at higher genus. So far, these higher genus are defined by these recursive differential equations of Gromov Witten, Chicote, and Vafa. But even on the B model side, this is mathematically challenging to phrase. So what I want to talk about today is some holomorphic way and algebraic way of characterizing these equations, and in this formulation there will be some algebra, Lie algebra that appears. In the hope that eventually, if you were able to find the same structure and give it an A model or a curve counting interpretation, then you will be able to work with higher genus mirror symmetry or prove it. Okay, so here's a summary and summary of the logic of my talk. So these higher genus objects, it was known since BCOV defined these objects that essentially if you take the Calabi Yau threefold and the Calabi Yau threefold has anything to do with some elliptic form, some elliptic curves, then you're back in some classical theory that you know and love, and that's the theory of quasi-modular forms. So it was shown in many works that these topological string partition functions for particular Calabi Yau threefolds can be written in terms of finite polynomials in terms of quasi-modular forms. But however, this only works, as I said, if there's some elliptic curve hidden in your geometry, or your geometry is simple enough such that everything just reduces to the classical theory of modular forms. However, what about the general story? So the general story was first put forward by Yamaguchi and Yau. For the quintic, they found that there is some differential ring of functions which has formal analogous properties of this ring of quasi-modular forms. And they showed that the FG can be written as polynomials in these. So this was generalized by myself and Dominic Legge for arbitrary Calabi Yau manifold with any dimensional moduli space. So of course, this only puts the things on formal differential geometric equal footing as modular forms. So what we did last year, that's the things that Emmanuel talked about. If you're claiming that this is the general thing, then it should better, in the specific cases where you know that it gives you quasi-modular forms, it should reproduce these. And this is what Emmanuel talked about. So whenever you pick your Calabi Yau such that there is some elliptic curve, either it's elliptically fibered or it's non-compact and the whole data is captured by some curve, then actually these polynomial generators or this differential ring reduces to what you know already. But furthermore, it gives you something new otherwise. So this something new otherwise was independently also discovered by Movasati. And furthermore, so the one work, another work by Movasati that we want to generalize. So what he did for the quasi-modular forms attached to an elliptic curve, so he gave a differential geometric interpretation of these. If you didn't know about these quasi-modular forms, then you could go to some higher dimensional moduli space attached to an elliptic curve, such that these quasi-modular forms would be distinguished vector fields in that space. I'll talk more about this. And what I'm going to talk about today is just doing the same procedure for Calabi Yau threefolds. So put this more general ring of functions on some more formal equal footing as the quasi-modular forms. Okay, so here's the outline of my talk. So I'm going to spend some time just talking about the physics origin of the variation problem that we use on both sides. So if in all the talks previously we were happy with just the phrase by mirror symmetry this happens, then you can safely not skip all of this. But I want to use this to motivate that there is actually more structure hidden in there that I want to uncover. Okay, so I'm going to start with the origin of mirror symmetry, and I want to think about the origin in two-dimensional n equals 2, 2 superconformal field theory. So what is an n equals 2 superconformal field theory? So a conformal field theory, this is the energy momentum tensor. Z would be some local coordinate in 2 dimensions. And this T would generate the usual Virasoro algebra. N equals 2 refers that there are 2 supersymmetric extensions. So these are 2 other currents which have a different conformal weight. So the conformal weight is just telling me the weight of how these objects transform under coordinate change. And furthermore, there is something called the U1 current. And to this one is associated a charge, which enables me to distinguish these 2 things by plus and minus. So these are the four objects. They satisfy some current algebra, which I didn't write down. It's not particularly illuminating. Furthermore, you can decompose, you can Fourier expand all of these currents, and you get these coefficients here, what we call the modes. And then this superconformal algebra you can also write down in terms of the modes, and then you get some algebra that you're more familiar how to deal with. Okay, by how to deal with, I mean you want to describe the representation theory of this algebra. So you do it in the usual way, so you're looking for some highest weight states, and these are usually the ones which are annihilated by all the positive modes of all these currents here. So I want to split all of these into the positive ones and into the negative ones. I want to require that there are some distinguished states which are annihilated by all the positive ones, and then start building up the representation theory using the negative modes. Okay, and then you can label these highest weight states by the eigenvalues of the Cartan subalgebra. In this case, it's the zero mode of the energy momentum tensor, which gives this eigenvalue h, and it's the zero mode of this current, which gives some eigenvalue q, which I'll call charge from now on. And as is usual in conformal field theory, I'll be interchangeably talking about the states and the operators that create the states, because every state can be created by an operator. Okay, out of these highest weight states, these can be generically infinitely many. But it turns out there is a subset of these which is of particular interest. And the subset of these, so remember the highest weight states were annihilated by all the positive modes. If I require in addition these the highest weight states that are annihilated by the first negative of these G plus and G minus, so this will be just a subset of all the highest weight states. And I call these chiral and these ones anti-chiral. So this is just referring to this plus and minus label that I have here. Okay, now I have to tell you why do I want to restrict to this set of states. Okay, I want to restrict to this set of states because I can derive using the superconformal algebra that for these states there is a relation between the eigenvalues of the two Cartan subalgebra generators. And the relation is that h is equal to the absolute value of the charge half. Okay, for generic state which doesn't satisfy this condition, h will be strictly larger or equal to this condition. So if you're familiar with BPS states, so this is some bound condition which is the formal analog of BPSness, and I'm just picking out some particular states. So these are the analogs of BPS states. Or if you want to think of objects in the category, these will be the stable objects.
So is there a unique vacuum? Is the vacuum unique here?
The vacuum is unique up to scale.
Yeah.
So furthermore, so why did I pick up this state? So the first thing, there was some bound that was saturated. The second thing I can actually also show from the algebra, there are only finitely many of these. So the charge, so this is for Calabi Yau threefolds, or for the corresponding superconformal algebra, is bounded by 3. So there are only finitely many. Furthermore, the operator product expansion satisfies this relation here, which is called chiral ring relation. So there's a ring relation in addition. Okay, so far all of this story has been for just one n equals 2 superconformal algebra, but the underlying mirror symmetry is an n equals 2, 2. So it's just take 2 copies of the superconformal algebra. Physically, you think of one as the left moving and the other one as the right moving. And then what happens, you have 4 possible combinations of finite rings that you can look at. So rings of operators or some states which have a ring structure that you can look at. And these will be combining the anti-chiral with the chiral, or combining the chiral with the chiral, or vice versa. So just to put in the back of your mind, all of this will translate into cohomology of Calabi Yau's eventually, and you'll be more happy. But I'm just telling you where this comes from. Okay. So furthermore, I told you, I started the motivation by telling you, okay, I want to study deformation spaces of physical theories, and then eventually translate it into deformations of Calabi Yau threefold. So how does that come about? It turns out that another subset of these chiral ring are the ones which have charge 1, 1. So I told you before, the charges of these chiral ring elements in each sector can go from 0 to 3. So particular ones will have charge 1, 1, or with a negative sign. So I'm just picking up the chiral ones. And these are the ones that you can add to the defining action of your conformal field theory, or can you think of these as the things that will perturb the theory? So physically, this is actually deforming the theory. So physically, you can associate a moduli space of theories, and you can think of these objects as the things that will get you from one point in this moduli space of theories to another one. So also these are in this finite parallel ring. Okay, next step, I want to just focus on this interesting subset of states, which is finite. It contains the things that generate the deformations. So how do I do that? Okay, I want to truncate the whole representation theory just to this finite set of states. So you should say, okay, this sounds like a cohomology problem. So why don't I promote the operator that gave me the condition that selects these states to some cohomology operator? So depending on which ring you want to focus on, you'll promote different combinations of operators to be your cohomology operators. There's an additional step that you need to do. So eventually you want to formulate a topological field theory of cohomological type. So you have the cohomology operator. And you need to make sure, in addition, that also the energy momentum tensor will be cohomologically exact. And to do that, there's a procedure called twisting that you need to do. So you just change the definition of your energy momentum tensor. Okay, so now to the geometric translation. So this was just the two-dimensional superconformal algebra. You can find a representation of this algebra in terms of what is called a nonlinear sigma model. So you can consider maps from this two-dimension into some target space, and such that whatever you write down, the action that you write down for the maps and the interpretation you'll have for the maps should satisfy this algebra. So this was done by Witten. And actually, this anti-chiral ring gets translated into the cohomology of the space X. And the chiral ring also gets translated into the cohomology of some other space Y. So now I consider X and Y as two different target spaces of two different models. The only difference is P and Q are what I call the charges. So these go from 0 to 3. The only difference is that the way this B model sees the charges is a little bit different, and this is due to the holomorphic 3-0 form that you have on this slide. Okay, so this is this whole finite ring translation that I want to focus on, and now I want to match things on the two sides. So in particular, I also want to be able to put coordinates on the two sides. So the way this works is I want to be able to choose some distinguished coordinates. So the distinguished coordinates on the A model side will be measuring the volumes of two cycles using a complexified Kähler form. So by this calligraphic J, this is a 2 form, and this is I times the Kähler form. On the other side, I'll be focusing on the middle dimensional cohomology, and I want to be able to define coordinates which exactly match these T's, and I want to find these coordinates by using the holomorphic 3-0 form, and I want to be able to match these things here. So how am I going to do that? So in order to do that, I want to study some structure on this moduli space, and I want to see how this structure varies. So the structure that I'm focusing on is the closure of the deformations, because eventually I'm interested in the deformations under these chiral ring relations. So I want to have all the 1,1 charges inside the thing I'm going to study. And I'm going to think of the closure of this. So here I have the 1, 1 charges. By this chiral ring relations, I have to include also all the 2, 2 charges. And I have to include the 0, 0 charge part. And there's also some 3, 3 charge part, which is some top form. There is something called the topological metric, which is a pairing between the charge 1 and the charge 2 elements in this thing, which is constant. Now I want to collect all the states that are created by these operators and think of these as forming some bundle over the moduli space that I have. So here I just said, okay, this will be the space of all the states created by the 0, 0, which is just 1. This is the one created by all the 1, 1 charges, 2, 2 charges, and 3, 3. And I want to identify this bundle, so just to get more, to be able to phrase it more geometrically. So the charge 0, I will identify with a line bundle. So as Professor Anderson has asked, the ground state is only unique up to some function, and this means that it's a section of a line bundle. All the charge 1 operators, I told you that these generate deformations of the theory, so I can identify these with elements in the tangent space of the moduli space. These ones I will call dual to these ones because I have this metric, and this one will be dual to this line bundle because there is also a pairing between these. Right, so my goal now is just stick to this structure and now start to talk about the mathematical incarnation of this structure.
Could you just repeat why the L gets tensored onto Cm?
Oh, because the same redundancy I have of multiplying with an arbitrary function, I also have in the next space. Because, yeah. So here, the EI, so the charge 1, 1, which will be elements in here, will be obtained from acting with the charge 1, 1 on the E0, and it will sort of inherit this redundancy by scale from the state it came from. Okay, so now just to recap, so I chose these ones such that this is the closure of this ring relations. So let me just phrase, if I take elements in all of these spaces and put them in the following form, what the ring relations and all the topological metric relations will look like in a matrix form. Okay, so this matrix form is going to be important because we're going to recuperate this in both sides of mirror symmetry. So now remember these deformations. So the phi I can add to the action with some parameters. And if I want to think about the action of these deformations, then I can also think about inserting these is obtained by a derivative with respect to the parameter. So here's where geometry comes in. Because now I can think of this structure as actually some partial derivative acting here. And I can think of this whole thing here as some connection matrix. And indeed, so if I think about this this way, I think about this as vector E. Then this will tell me nothing but there is some flat connection, which, and this E is a flat section with respect to this flat connection. And this will actually translate into the Gauss Manin connection. Before going to the geometric translation even more, let me introduce yet more structure that we have here. So the one thing I want to do is replace these dual states that I had here with what is physically called CPT conjugate. Mathematically, you should think of these as the holomorphic, the anti-holomorphic counterparts of the ones that I have up there. So this construction is due to Chicotti and Baffa. So what this effectively does for you is replacing the topological metric, which was pairing the charge 1 and the charge 2 operators, with some other Hermitian metric, JAB bar. So now the spaces that I call dual, because there was a pairing with a topological metric, will actually become complex conjugates of the spaces I had here. So now, why would I do that? So first of all, the chiral ring relations, which I wrote down earlier. So the chiral deformations will just look as they looked before, except that there will be this Hermitian metric appearing here. But all of a sudden, I also have the anti-chiral ring appearing. So I can also tell you what the anti-chiral ring action on this basis will be, and this will be of this lower triangular form. So let's translate this back into geometry. Remember, you could add both of these operators with some parameters, t and t bar, which are not necessarily complex conjugates. So geometrically, what this becomes are what are called the TT star equations. So you should think of this covariant DI, so I'll tell you in a moment what covariant means. But covariant will be the thing replacing, just inserting this guy or the other one. And C, you should think of this whole matrix. So what Chicote and Daffa did is put forward this set of equations. And these set of equations actually mean that, again, there is some flat connection. So there is a flat TT star connection on this moduli space, or on this bundle.
Completely flat.
Completely flat, yes. So, okay, so what does this translate into mathematically? So if you're on the B model side, as I told you, this bundle, this deformation bundle that I focused on, will translate into the middle cohomology of your Calabi Yau Y. So for the middle cohomology, you can have the Hodge decomposition, but as you know, the Hodge decomposition spaces do not vary holomorphically. So the whole bundle is the whole bundle is trivial all over modular space, but the decomposition, I have to specify some base point where I want to do the decomposition, and as I move the base point, these spaces will not vary in a holomorphic way. However, there is some other thing that you can study which varies holomorphically, and this is what is called the Hodge filtration. So the Hodge filtration will be just sums of these spaces such that they vary holomorphically. And you can recover one from the other. So in particular, you can recover the decomposition from the filtration and the complex conjugate filtration. There is, for this filtration, there is a holomorphic flat connection, and that's the Gauss Manin connection. So just schematically how this filtration works, or how you can keep track of deformations in the complex structure moduli space. There's a unique holomorphic 3,0 form on the Calabi Yau threefold. And as soon as you act with the Gauss Manin connection on this, so you can think of this as the effect of an infinitesimal deformation, then this holomorphic 3,0 form will pick up 2,1 pieces, but it will still remain holomorphic. If you do act on it again, it will pick up pieces from the next Hodge decomposition space, but it will also have pieces in the previous spaces, and so on, until in the last step, you generate everything. So if you go one step further, if you take another derivative, then the form you will get will also be in this space. So in particular, it should be a linear combination of everything you had before. Okay. So this linear combination translates into a Picard-Fuchs system of differential equations, which we heard about, talk about this morning. For example, for the mirror quintic family, so Z is just a perturbation monomial of the generic quintic in P4. So of the mirror side, this is the Picard-Fuchs operator. And just to illustrate this, you can actually, so using different methods, find out what this linear combination will be. So I told you that the fourth time you take a derivative will be expressible as a linear combination of everything you had before. And I tried to look whether this is actually describing the physical problem I started with. So I choose the elements in these filtration spaces in this way. So I put in this choice of the C. C is some rational function on the moduli space in this form, but it doesn't quite recover this strictly upper triangular structure that I advertised in the beginning. So what this is telling you is actually this is not the good choice of filtration that you started with, and it's also not a good choice of coordinates you have. So in terms of this coordinate and this choice, you do not recover what you wanted. But if
just a question about omega C vector. Is that the one we see on the left or something else? It's the same as the one.
Yeah, exactly.
Oh,
it's exactly the same one. Yeah. So, and this is just telling you the linear combinations. Okay. So you can get to the structure that you want by changing the choice of filtration that you had, changing different coordinates, and there are more changes you have to do, but I'm just doing this schematically. And then you can compute how this connection matrix changes as you change this choice. And you can enforce it to be of the form that you want. In doing so, all the quantities that you introduce here will be the ones that exactly mimic the physical problem that you had. And these will be, from the B model side, the good coordinates that you need to consider, because you know that this connects to physics, and physics will eventually also connect to the A model side. Okay, so if you do this, you get some coordinates t. So if you now consider the period vector of the holomorphic 3-0 form after having done this procedure, and then by the physics identification, you identify these quantities with, on the A model side, volumes of 0, 2, 4, and 6 cycle. Okay. And if you do this procedure for the quintic, you get the following. You get just some distinguished coordinate, which will be called the mirror map, because it's the special coordinate on this moduli space which maps to the other side. And furthermore, this C here will encode the genus 0 Gromov Witten invariants. Okay, this was the holomorphic way of describing the V model. But I told you that there is also, from the physics point of view, there is also a way how to describe this non-holomorphic decomposition. So in the non-holomorphic decomposition, we replace these two spaces by the complex conjugates ones. And this also has an exact analog in the variational Hodge structure. And this is exactly taking the Hodge decomposition. So these two spaces will be the complex conjugates of these two ones. Okay. So now there is a structure, or there is some differential geometric structure, which is called special geometry, which allows you to define covariant derivatives which exactly map elements from each of the space strictly into elements of the next space. Remember, with the Gauss Manin connection, I was just getting some combination of everything I had before and additional stuff. But there is some other structure which is really respecting this Hodge decomposition. So this structure is special geometry. And special geometry is given by a metric on L. So you can think of the holomorphic 3-0 form, and then this metric on L will be pairing omega with omega bar. So this is pairing these two spaces. And this K defines a Kähler metric on the moduli space, Gij bar. And now these covariant derivatives will be covariant with respect to both of these, with respect to both of these metrics. TheCijk is a purely holomorphic object that you get from taking omega and 3 times the derivative of omega.
Just a question for
Yeah.
Ron. The DI, is that the same as taking the Gauss Manin connection and then projecting onto that part where it goes to, or it's different data?
It's different data because it's inherently non-holomorphic. So what DI is doing for you, so remember in the here, if you just took the Gauss Manin, then you would get always also parts of the new form will be in this old space.
Yeah.
What this DI is doing for you is from this element we will subtract the 3,0 form, or we will subtract it in a non-holomorphic way.
Yeah, but you remove the H30 part and you end it in 201.
Exactly, yeah.
But do they agree then? That was my question actually.
Yes.
Do they agree? If I take this number set, omega 30 set, and project onto H21, do I get the DI that I saw before?
Yes, but taking the DI, the functions that you will use to multiply, to subtract these things will be non-holomorphic. Yeah. But there is a notion of a holomorphic limit, and then things become holomorphic again. So with the DI, generically you will get some non-holomorphic element in the next space.
Right.
Okay, and now with these DIs, so this is what I just said. You can start with a holomorphic 3,0 form. What the DI is doing for you is mapping this exactly to a 2,1 form with no additional pieces. And if you go on and on, then the way these covariant derivatives act is actually in each step it will generate some element in the next Hodge decomposition space. If you put all of these relations again in this form, then you will see that this also mimics the CFT structure, but now in a holomorphic, non-holomorphic way. So we're pairing the holomorphic objects with the non-holomorphic objects. So in particular, there's no particular reason why the connection should have started, why I should have started from the holomorphic 3-0 form and started spanning all the other spaces. I could have also gone the other way around. So from the point of view of the geometry, the Hermitian metric, this metric on the line bundle was on completely equal footing on both sides. So I could have also taken the covariant derivative with respect to the so the 0,1 part of this connection and gone the other way, and I would have gotten this matrix. So the question I want to answer today is what is this information? What is this extra information in terms of variation of Hodge structure for the filtration? So you don't have this part in the filtration. You only have holomorphic variation, but you don't have the non-holomorphic one. So the translation of this deformation bundle to the A model side, so I will not talk too much about this, but this is the thing where mathematically you had to work hard in order to define. So I just wanted formally something, also define some connection which maps elements now of the even cohomology. If you take an element here, you want to map it in the next space, and so on. And you can just define it, so eta 0 will be an element inside this space. You want to map it into the next element, and so on. But now the tricky part is theCijk that you need to define in order to match the physics prediction turn out to be complicated mathematical objects. The first part is easy, so this is a triple intersection. You can think of it as triple intersection of divisors, or taking the wedge product of two forms and integrating over the Calabi Yau. And this part here, so defining what the physics outcome would be, you have to define that there is an infinite series which gives you the Gromov Witten invariants. Okay, so now I come to the polynomial structure. So you should keep in the back of your mind that I want to answer the question, what is the non-holomorphic derivative? What is this data in terms of the variation of the holomorphic variation of Hodge structure? So again, this is the data that defines special geometry. I want to consider the variation of this deformation bundle over the moduli space. And as I said, physics would tell you that this should be a structure that is on both sides of mirror symmetry. This was the metric on the line bundle, which defines a Kähler metric on the manifold. And these were called as holomorphic Yukawa or Griffiths-Yukawa couplings. This is again the flat connection that I described, which was coming from the TT star equations or from the CFT Carroll ring relations. What this is actually telling you, if you write it out, this is telling you that the curvature of the Kähler, the Hermitian Kähler metric that you define in the moduli space is of very restrictive type. So it is of restrictive type because it involves the pairing of this holomorphic Yukawa couplings with the anti-holomorphic Yukawa couplings. So now I just state the holomorphic anomaly equation. So as I told you, these FGs are global objects on the moduli space. And what Bershetsky, Chicote, Iburi, and Waffa found is that they satisfy some non-trivial equations under the d-bar derivative. This is called anomaly because, strictly speaking, the insertion or the derivative with respect to the bar would correspond in the topological cohomological field theory to inserting a cohomologically trivial element. But nevertheless, it gives some outcome because there is some integration over moduli spaces of Riemann surfaces involved, and the contributions come from the boundary of this. But I won't get into too much detail. So this is the structure is strictly differential. So it's a differential equation which is strictly recursive in the genus. So everything that appears on the right-hand side is of lower genus than what appears on the left-hand side. What BCOV further did is introduce, so part of the TT star equations will also tell you that for holomorphic Yukawa coupling as well as for the anti-holomorphic Yukawa coupling, that locally you can write this as a third derivative of something, so you can define some potential for that. And I call these objects S and Si and Sij, such that if you take 3 derivatives, you get back to this non-holomorphic Yukawa coupling. And then what I did is, okay, this C bar that appears in the equation. So I thought, okay, if it's strictly recursive in the genus, so why don't we try to solve this? So let's try to integrate out the d bar derivative from both sides. So let's first write this thing as a derivative of this object, and then integrate out the d bar from both sides. You need to make up for this by acting with d bar on these things, and what happens is that you'll keep using the special structure of this curvature. What I found, and surprisingly, that this leads to some Feynman diagram amplitude type expansion of the FGs, although this was not the thing that you put in. These Feynman diagrams where you interpret these objects as propagators and derivatives of the FGs as vertices. So this is wonderful because you could compute these higher genus objects and then take certain limits, and then you would have a way to compute, for example, higher genus Gromov Witten invariants, or to give predictions of what these should be. However, the Feynman diagrams were very tedious. And an enhancement or a simplification of this procedure was put forward by Yamaguchi and Yau for the quintic. What they did, okay, everything that happens in this derivation is that you keep acting with derivatives and then you keep hitting connection pieces and so on. So what Yamaguchi and Yau proposed, okay, if you take the connections that appear in this setup and you keep taking multi-derivatives of that, then this will be just some random new functions on your moduli space. And there'll be infinitely many if you take infinitely many derivatives of these objects. But what I found is actually this is not true. There are only finitely many, and then everything else you can express in terms of these. And they found that the FG are polynomial in these objects. So later on, in work of mine with Dominic Lenger, we generalized this, and we found that actually there are these 3 objects which are potentials for the non-holomorphic Yukawa coupling, and some derivative of the connection of the line bundle metric give you generators for any Calabi Yau manifold with arbitrary dimensional moduli space. And we proved that the FG are degree 3G minus 3 generators in these objects if you assign some weights to them. So the way to prove this is first you have to show that taking derivatives of these generators will eventually also close on these. So this puts forward some differential ring of functions on the moduli space. And then the rest will be proved inductively, so you just start with your starting F1, and you show that from the structure of the holomorphic anomaly equation, everything that will happen will generate higher degree polynomials.
What is your precise assumption here for this rational function in algebraic moduli?
Yeah, this is not mathematically rigorous at all. Okay. So the assumption is that there is an analogy to quasi-modular forms. So the assumption is that all the objects which are not purely holomorphic, so all of these are non-holomorphic objects, that all of these capture everything that is inherently transcendental in the moduli space. So if you think of the FG just as a function on the moduli space, then it's only given as an infinite series, but you can't. So the assumption is that everything here, everything transcendental will be packaged in the polynomial generators, and everything else will be rational function in the analog of the J invariant. So analogy is really that everything that you can formulate on the moduli space of an elliptic curve, which is transcendental, will have to be formulated in terms of Eisenstein series E2, which is not modular, which requires some non-holomorphic completion. And everything that is just modular will be a rational function in E4 and E6, or a rational function in the J invariant. So the assumption is, so I'll also tell you that there is some freedom in choosing these generators precisely. The assumption is that you can always find a choice such that everything that is that you can only express in terms of series will be packaged inside here.
So this is just a formula. So what is now mathematical?
Nothing. So not even with this.
So that's a conjecture, so to speak.
Yeah, exactly. Yeah. So yeah. So these the differential ring. So this is the derivation of these is rigorous, showing that so everything that is blue here are rational holomorphic functions. So that these C's are rational holomorphic. This is also rigorous. But then that there is a choice of these guys such that everything else will also be rational. This is just a case-by-case study. The further thing, which is not proved, so at the end of the day, everything you get out of this procedure will be up to the kernel of this operator. So another thing that we expect is when you package everything transcendental in these polynomials, then also the kernel will be just a rational function. But also this we cannot, we don't know. We don't know how to prove. Because, so the inherent problem, there is no mathematical definition of what FG is. And the only thing that we use as a definition mathematically would be, okay, this is the object that satisfies the set of equation. So it is inherently has an ambiguity, which is the kernel of this thing. So this ambiguity is fixed by expected boundary behavior, but there is no way to make this, or at least I don't know the way to make this.
And sets are coordinates on the modular space, right?
Yes. Yeah. So in the one-dimensional space, I just wrote Z, and multi-dimensional, I would be writing Zi. Okay. So you start from the initial correlation function, and then you show by induction that all the other ones are polynomial. And now you can say, okay, the FG, everything that is non-holomorphic will be expressed in terms of polynomials. So the holomorphic anomaly equation can be written down as derivatives with respect to these polynomial generators. So, one of the equations you can use to redefine generators, and you get some redefinition. And in terms of the redefinition, you will see that all the freedom you have in choosing generators will be adding purely holomorphic functions to some choice that you've already made. So there is some redundancy there. Okay. So computationally, so apart from the formal analogy with quasi-modular forms, computationally this enhances computations a lot, and is essentially due to, it's very hard to write down Feynman diagrams already at genus 2 or genus 3, but these polynomial formulation you can just put in a computer. And in fact, so if you take the quintic as a benchmark, then Huang and Clem showed that this can be solved to very high genus using this procedure. Okay, this is what Emanuel Scheidegger talked about. You can now take these differential rings, which are there for any Calabi Yau manifold, and you can focus on some Calabi Yau manifolds where you expect some elliptic curve to appear, and you will see that this differential ring agrees with the differential ring of quasi-modular forms. There was an independent, so Hossein Movasati in 2010 was asking what is the analog of the Eisenstein series for the quintic, and he derived in a purely holomorphic way using the Gauss Manin connection a set of functions which form a ring, and this turns out to exactly agree with what we had there. Okay, so let me come to the new part. So this is the work in progress. So as I told you, now you can think of the FG as a polynomial in terms of these, and everything becomes much simpler. So FG, just on the moduli space, was some terribly complicated function that you should think of as an infinite series, as an expansion in the moduli space. In terms of the polymers, it becomes some finite polynomial expression. So now you can ask the question, okay, can I think about this more algebraically? Can I think of these polynomial generators as giving me coordinates on some bigger space where things become nicer? And the answer turns out to be yes. And the guiding principle is work of Hossein Movasati, who did this same procedure for the elliptic curve. So we found if for the elliptic curve, you just have a one-dimensional complex structure moduli space. If you enhance the moduli space to the moduli space of an elliptic curve plus a choice of differentials respecting the Hodge filtration, then you get a three-dimensional space. And then he showed that coordinates on this three-dimensional space correspond to the Eisenstein series. Furthermore, there is a Lie algebra, so you can think of vector fields in this bigger space. And particular combinations will generate some constant Lie algebra, and in this case it was SL2C. So now we're asking, can we obtain the same thing for Calabi Yau threefolds? So the answer is yes, and the way to do this is to enhance the moduli space of the Calabi Yau and to also enhance it with a choice of filtration. So remember, if I just use arbitrary coordinates, start with a holomorphic 3-0 form, I can start generating elements in the next filtration spaces, just in an arbitrary way. In this choice, I chose the elements in such a way such that their symplectic intersection will be constant. But I told you that I can also span the filtration by acting with these covariant derivatives. And this will give me some nicer way of spanning the filtration. So this is a different choice of the filtration using these covariant derivatives. And now what happens is, again, I have multi-derivatives acting on things. So what will happen if I try to express this basis in the older one, I will start generating the polynomial generators. So both of the bases were chosen such that their intersection, symplectic intersection, is constant. So this was one thing I put in by hand. And now I want to formulate the matrix which relates these two choices. So the matrix, as I told you, relating this choice to the other one. So changing the choices has to respect the filtration. This is why this matrix is lower triangular. And all the entries of this matrix will be phrased in terms of the polynomial generators. So some slight modifications, which I didn't write down here. So this really tells you can think of these polynomial generators as coordinates or as parameterizing the different choices of filtrations that you have. There's a further step in coming from this non-holomorphic choice of filtration. As I told you before, there is some procedure taking the holomorphic limit in order to get eventually to a holomorphic, what is called a flat basis, which has this particular form of the period matrix. Because this is the form that eventually you also expect to appear on the A-maps. So again, the logic is start with a random choice of filtration and relate it to the choice of filtration that you want for mirror symmetry. And in between, what we used is this non-holomorphic detour, because this is what generated these polynomial generators for us. Okay, so yes, we can think of a bigger space. The bigger space is the Calabi Yau plus a choice of forms. This bigger space has a much higher dimension than the moduli space. So the moduli space dimension was n. And this bigger dimension, parameterized by the polynomial generators, will correspond to the dimension of an algebraic group. So the algebraic group is precisely the one acting on this filtration spaces, doing what you wanted to do. You want to change the filtration spaces, respecting the filtration and the constancy of this matrix. Now we can think of the Lie algebra of this group. And what we show is there are combinations of vector fields along the polynomial generators, such that if you compose these with the Gauss Manin connection, it will give you generators of this Lie algebra. And this is the new thing that we have. So if you just compute derivatives along the generators in this bigger space, then generically you will get some non-constant matrices. But what we show is that there is combinations of these which give you constant matrices. And these constant matrices generate the Lie algebra of this algebraic group. Okay, so in addition to all these non-holomorphic things, you can add the holomorphic derivations, but these will be not constant matrices because you have these C's appearing here. So eventually you can just compute the commutators of this Lie algebra and put it in this form. But eventually what we wanted to do is just a holomorphic formulation of the holomorphic anomaly equation. And now if you treat all the FGs as just being formal polynomial expressions in this bigger space, you can formulate the anomaly equation now really by the action of vector fields in this bigger space. And it will become many more equations. So there are actually missing equations here which appear. If you take the generating function of all of these, then the holomorphic anomaly equation becomes a whole set of functions. Okay, so this is where I want to end. So again, the logic was there is some differential ring of functions on the moduli space of an arbitrary Calabi Yau manifold, which sometimes reduces to quasi-modular forms for particular Calabi Yau manifolds. But more generally, it gives you something new. And if you take these functions seriously and think of them as coordinates on a bigger space, and think about vector fields in this bigger space, then this gives you some Lie algebra. This gives you some holomorphic algebraic formulation of the holomorphic anomaly equation. And up to now, we don't have application, but we expect that this will provide an easier method to maybe recover the same invariant structure on the A model side. And since there are many people who know integrability and so on, I was hoping maybe there'll be some input on that. So physically, this will be interesting because you have some new structure arising, so you can start identifying it with different setups where this happens. Okay, thanks a lot.
Any questions?
Yeah, so is there any relation between this holomorphic anomaly equation and topological recursion?
Yes, yes. So there's been
part of topological recursion?
so again, topological recursion is a case which only treats curves.
Yes.
So if you mean the inner or outside.
Yes.
So there has been conjecturally that by Bouchard, Marino, Clem, and Pasquetti that the same topological recursion, because for some non-compact Calabi Yau manifolds, the mirror side effectively reduces to a curve. So they applied the topological recursion to the curve, and it gave Gromov Witten invariants. But the topological recursion is from the outset formulated in a symplectic way. And I think that there's been a paper by Marino which interchanges the symplectic formulation with the non-holomorphic formulation and showing that, I don't know, maybe, I don't know if you know maybe what this is.
No, I don't know the answer to that.
Yeah, so I think there has been work showing, or I don't know to which degree of rigor, that this should be the same structure, but again, this is something that only applies to curves. So the topological recursion only applies to curves, and people took it and applied it to Calabi Yau threefolds, non-compact Calabi Yau threefolds, where the essential data is inside curves. So at the end of the day, it should be a sub, again, the realm of quasi-modular forms and not the general setting. So there is no topological recursion for Calabi Yau threefold, for the quintic, for instance. Yes?
Yeah, so we didn't interpret the holomorphic, what's it called? Holomorphic anomaly equations as the heat equation for the compact group, right? So you only differentiate in holomorphic directions.
Yeah.
But we saw that at the beginning of your talk, you had derivatives both in the holomorphic and the anti-holomorphic directions. The connections is non-trivial in both directions.
Yeah.
And I was just wondering if that fits with the SL2C story. Because if one looks at Witten's paper on SL2C quantum two ensemble theory, you will actually see a connection that is exactly, I mean, it's very similar to what you have. It differentiates in the holomorphic direction and it differentiates non-trivially also in the anti-holomorphic direction.
Yeah, maybe there are connections, but I don't know how to see them.
Any other questions? If not, let's thanks. So the next talk will be a Swiss surgeon.